let's continue. So we saw these two inequalities. The rephrased Chebyshev one, when the mean of the random variables is 0. Well, here we bound the sum of, what do we bound? We use inequalities involved the sum of random variables. And what is this thing here? What is this? Maximum of the sum, but what kind of maximum of sum? Let's go with the proof of congruous inequality. Which, let's try to recall, is a squared the probability that the maximum for k less than n of the absolute value of the sum sk is larger than a is bounded by the variance, which is in turn bounded by the second moment. Or not? No, in this case, no, it was the first inequality involving this thing here. Let's fix a positive and consider n greater than 1. Define n of omega to be the infimum of the set k greater than 1 such that the absolute value of the realization sk is greater than a. For any omega. And note that n of omega is k if and only if the absolute value of sk is less than omega. Is less than a. It's actually greater. Sto dicendo tante cose a caso. So we fix a, we define n of omega to be the infimum of the index k such that the sum is greater than the value a. And we notice that this n of omega is k if this is greater than a, and as j of omega is less than a for any j less than k. Then we have that the indicator over the set in which n equals k is a function of x1, xn, and now for k less than n, define u, which is this random variable. And v, the difference between sk and sj, right? No, sn, sn. The difference between sn and sk. Which are independent because u independent of v, because they are functions of x1, xn, xn plus 1, x1 xk, xk plus 1, xn, respectively. And observe that the expectation of u times v, since they are independent, their covariance is 0, and therefore the expectation of sk times the indicator when n equal k equals k of Sn minus sk is 0. Okay, this can be useful. This inequality can be useful when we consider a sum of random variables. Like, for example, this can be considered like a sum. We have some value a, and we want to know when the maximum, the probability that the maximum is larger than this threshold. And to do this, we consider the variance of the sum. This can be an interesting interpretation. So moreover, Sn squared which can be expressed as sk Sn minus sk, all of this squared this thing is greater than sk squared plus 2sk Sn minus sk. This gets squared, this gets squared, and so here we don't consider, and then we have 2 times this, which is this. So here we don't consider the square part of this is greater than that. note that the absolute value of sk squared is greater than a squared when this thing here holds. And then the expectation of Sn squared times the indicator when n equals k is greater than a squared times the expectation of, let me put it in as a display, the expectation of Sn squared times the indicator when n equals k is greater than a squared times the expectation of the indicator when n is less than k plus 2 times the expectation. Here it's actually equal k, I think. Of sk Sn minus sk times the indicator when n equals k and this thing here is 0. Why? Because we saw it here. They are independent. And so this is a squared times the probability that n equals k. Finally, summing both sides for k less than n, we have that a squared probability that n is less than k, less than n by n, well, is less than the expectation of Sn squared, the indicator n equals n, n greater than n. Which is the variance of Sn. variance. Okay, so maybe I think that the statement was wrong in some way. Why do we have greater here? Or maybe it's just an alternative formulation. Here we have k less than n. Here we have, well, it's an alternative formulation. Let's go with the proposition. Let's take a look at this. Xn, consider a sequence Xn independent with mean 0. If the sum of the variances converges, then the sum of the values of the variables also converges almost surely. If Xn is a bounded sequence, of independent random variables with same distribution, well, if the sum over n of Xn minus An is finite, almost surely, for some sequence An of real numbers, then the sum of the variances is also bounded. Okay, now we have Kolmogorov 3-series theorem. K3s. Consider Xn independent. We have that the sum of the random variables is finite if and only if we have the following three series converge the sum over n of the probability that xn is different from yn, where yn is xn times the indicator that xn in absolute value is less than b, maybe, I don't know. I don't know if this is correct. Then you have the sum of the variances of yn and the sum of the expectations, which actually should be the second one. Let me check this. Here it doesn't say. Okay. Let's try to get more familiar with this. So Kolmogorov 3-series theorem. If we have a sequence xn of independent random variables, we have that the sum of them converges almost surely if and only if the following three series converge. The sum over n of the probability of xn different from yn, where yn is xn, the indicator that the absolute value of xn is larger than, or is smaller than b. The sum of the expectations and the sum of the variances. Now we have a remark on the law of large numbers, which says that xn bar converges to expectation of x. It tells you that the random variable converging to x, it tells you that the random variable converging to a degenerate random variable. So it says that the sequence the mean converges to a number, so we lose the variability in the limit. Okay. So let's start with the central limit theorems. this is the simplest version. Consider xi a sequence of independent random variables with same distribution. So IAD, oops. Well, let's just xi IAD with common finite mean and variance. Then we have that Zn, well, let's put it like this. Zn which is this quantity here, Sn minus Na over square root of Nb, where Sn is the sum of the random variables, of course from 1 to n. This converges in distribution to a standard normal random variable between 0 and variance 1. Well, if it's standard normal. Let me try it again. So xi IAD, common mean, common variance, then Zn, which is Sn minus Na over root of Na Nb, converges to a normal 0, 1. The usual way to prove this theorem is using Levy something theorem, which says that convergence of characteristic functions is equivalent to convergence in distribution, which is, I think we saw it, right? Well, in any case, we want to extend this to more general setting, but before that we need to introduce some concepts. So okay, now if A equals 0, B equals 1, so the mean is 0 and the variance is 1, then Zn, which was Sn, this is Sn minus Na, Na goes away, over square root of n times b, which is 1, so we have this left. So, and Zn is the sum of independent random variables which are xn1 is x1 over root of n, xn2 is x1 plus x2, no, it says over root of n, and so on. N is fixed, and as n grows they get smaller, so the summands approach to 0 as n goes to infinity, but for any n, Zn has anyway been 0 and variance 1. So these become smaller and smaller. So the sum of random variables stays stable in some sense. Bo. Here it says that we need a special structure to handle this kind of sequence of small independent random variables. And this structure is called triangular array. A triangular array is an infinite matrix where the entries are real valued random variables. Furthermore, for any n, there exists an integer kn, infinite matrix of real valued random variables. Moreover, there exists, for any n, there exists an integer kn such that kn is 0. X of kn is 0. For j greater than kn. So the random variables are 0 for all columns at the right side of kn. And the sequence of indices kn is increasing to infinity. So this object is like this. We call it briefly like this. This is x11, x12, x13, and so on, x21, x22, x23, xkn, xnj, xkn. There is some index, let's put it for example here, after which all these are 0. And for example, then it becomes this, and all the others are 0, then it becomes this. Because the sequence kn is increasing. But the sequence, okay. Now define Zn to be the sum of the xij's, xnj's. So j is the column and rows j columns. For j from 1 to kn. So we sum over the columns which have some values. And now as assumption, as hypothesis, the random variables on each row are independent between them. Among them. I don't really know how we use this structure, but at least it's more clear to me than the first time I saw it. So here we have some contribution. Here we have some contribution. Contribution, contribution, contribution. And here zeros, zeros. With this said, let's state the Lyapunov central limit theorem. And as a small anecdote, I think I have read on the Wikipedia page that Lyapunov has shot himself, and he died 3 days later. This because her wife was sick, I think. I don't remember if it was Lyapunov or Lindbergh, but I think it was Lyapunov. In any case, suppose that the expectation of x and j is 0 for any n and j. So the expectation of each random variable in the triangular array is 0. And the variance of Zn is 1. Where Zn, remember, was the sum over j of x and j. This for any n. So for any row. And the limit as n grows of the sum over j of the expectation of the cube of x and j is 0 So the expectation of each random variable in the triangular array is 0. The variance of each row is 1, and the limit of the sum of the expectations at the cube is 0. Now my question is, why cube and not square? This should be seen in the proof, but I still don't know why. Then the conclusion of the theorem is that Zn converges in distribution to a random variable z, which is standard normal. So what is the difference with the Moivre Laplace? Here we are not assuming anything. Well, we are still assuming things about the expectation, the variance, but we are not assuming independence. Let's see the remark here. So we have replaced the condition on the variance. I don't see how we replaced it, but the generalization lays in the fact that we can use the framework of the triangular array in which the random variables may vary between rows. Let's try just to visualize the triangular array again. And I would like to make some kind of concrete example. So we have this is Z1, this is Z2, this is Z3. Or not, because it's the sum over the columns. So this is Z1, Z2, Z3. The expectation of x and j is 0. And let's consider, for example, Bernoulli random variables. Let's say after this is 0, this is 0, this is 0, etc. After this 0, 0. After this 0, 0, 0, blah blah blah. This is plus 1. This is 1, this is 1, 1, 1, 1. Can we say this? I mean, I'm considering the realization. And Zn, this becomes a normal 0, 1, as well as this and this. Let me state the theorem again for memory, to help memory. Consider, I already forgot the statement. Suppose x and j, the expectation of x and j to be 0 for any n and j. The variance of Zn to be 1 for any n, and that the limit as n goes to infinity of the expectation of x and j to the third power is 0. Then Zn converge is distributed or converges in distribution as normal 0, 1. Well, I actually has a distribution of a normal 0, 1. No, converges in distribution to Z, which is distributed as 0, 1. And to prove this, we rely on Lindeberg's lemma. Let y1, yk be independent random variables with mean 0. And let S be the sum of them. Up to k here, it says. Well, yeah, because we are considering k of them. Let us further assume that the variance of S is 1. And let f be a function which can be differentiated 3 times, bounded and continuous. I will put it in C3. Bounded. Such that the absolute value of the third derivative of f is less than some constant c in the real numbers, positive. Then we have this thing. The difference between the expectation of f applied to S and the expectation of f applied to Z is bounded by the sum of the expectations of yj to the third power, where Z is a normal 0, 1. So the distribution, so the distance between S and Z is not very large in terms of realizations, I guess. Which in turn means that if the realizations are not very far, the distributions should not be very far, because the central limit involves convergence in distribution to a normal. So we have that the random variables are independent with mean 0 and variance 1. Well, but this is just a lemma, it's not a... The proof is very long. Which suggests me to take another break. Because long proofs are tedious.